Prova a tomar la nana. Tomar la nana. Okay, we ready? Well, so the last part of the first lesson, we're going to see an example of what is a very low-level example of what is an abstract machine. All right. Thank you. So, prova tomar la nana. Well, in the last part, we are going to see an example of an abstract machine, the lowest level one, okay, in the hierarchy of a regular computer. Here we have a schema, a picture of what everybody knows, I guess. Do you want to try to tell us what is this? No, guys, somebody want to try? I mean, it's something that you have seen already. Yeah, almost. It's a CPU, it's a processor. It's the typical schema of a processor. We have, these are registers. Okay, this is as I say, this is at the lowest level abstract machine. It's called the physical machine, and here we have register. This is the PC, the program counter. Here is where the next instruction is stored. The next instruction to execute from from the language in input to the abstract machine, and then there are a series of registers that is like the internal memory of the machine. And then there is the ER. ER stands for instruction register. Is here where the instruction is stored after the fetch phase. If you remember the previous loop, first thing, the instruction to execute is fetched, and it is stored in this register. Then there is the ALU, the ALU is arithmetic logic unit. It is where all the primitive operation of the machine are implemented. In case of this machine that we are seeing here, a physical machine, these are implemented as circuits, okay? So are implemented in hardware. And then there are these two more registers that are, they take care about the data exchange, okay? These are data structure, if you remember before, for the control of the data exchange with main memory, with the external memory. Okay? Now, again, let's think again in the four, like before, the four groups of operation in data structure. We have operation for the primitive, the group of operation and constructs for the primitive operations. And this, for example, would correspond here to the arithmetic and logic unit. Okay, the arithmetic and logic unit is an implementation of all the operation, arithmetic and logic, of all the primitive operation, sum, conjunction. Okay, it is a hardware implementation by means of circuits. Okay, so this was the first group in this schema. It's this component, the first group in this list. Someone want to tell me what is this PC, program counter, stand for? I tell you again, program counter is a register that stores the address of the next instruction to execute. So in which group, which part of the interpreter this register is located. Exactly. You got it, guys, no? This is part of the sequence control. It's a data structure for the sequence control. And we have these two registers that, as I told you, are in charge of exchanging information. They are like temporary registers for exchange information with external memory, and these are clearly part of the third group for controlling data transfer. So what is missing here? We have primitive data processing. It was the ALU, and then we have for the control of the sequence of the program, and then we have structure for the data transfer. What about the fourth group? Not exactly. Okay, I'm sorry. This is a tricky question. Here there is no. We have first part, primitive instruction, arithmetic logic unit. Second group, control of the flow of the program counter. Data exchange, these two register. Why we don't have the fourth group? Because this is an extremely simple machine, okay? This machine does not need to allocate or deallocate memory, runtime memory, okay? So I told you before, for very simple machine, very low-level machine, they do not have construct to allocate memory. They do not have recursion, so you don't need to allocate memory, okay? Say that in practice, the situation is a bit different because in practice there is some multitasking so there is some allocation, some dynamic allocation. But again, this is an abstraction. This is a schema. In a very, very simple, there is no need for runtime allocation. Okay, so here we don't have register data structure of the fourth group. Now the interpreter, the fetch, decode, execution loop is implemented here in the control unit. Okay. So the control unit will interact with several components to perform the loop. Okay. Now, this is the hardware machine, the lowest level machine. It is implemented, as I say, at hardware by means of hardware. Instructions are encoded in hardware instruction, a sequence of logic circuits, combination of logic circuits, and there are three parts. Well, this classification was conceptual that I told you. But you can see this hardware machine as composed by three parts: memory, the language, and the interpreter. The interpreter is what we saw before, but what about memory? Memory is the register that you were mentioning. So memory is, the internal memory basically is this register plus this one. Technically also this, but you know, we're talking about memory to store, for example, the instruction. When you fetch the instruction, you store it in a register in the memory, and then when you store the operands, okay, this is what the internal memory for. Well, instruction, I already told you, instruction and data are the same from the machine point of view. They are just bits, but they are just bits that are interpreted differently. Typically, abstract machine of any level, very low level or very high level, they have few primitive types implemented, typically integer, reals, chars. Okay, but they are stored in the same way, sequence of bits, and when they are interpreted in different way depending on their type to get the wanted integer or the wanted real number and so on. So again, the distinction is conceptual, but for the machine there is no difference between data any kind of data and instruction. Then the language, the machine language provides you construct that must be translated by the interpreter. Okay, in case of the hardware machine, the language is very simple. Again, it's very simple means it's very low level, and instruction are things like this one. Add R1, R0, that means to add the content of the register R5, sorry, no R1, R5, to the content of the register R0. Or there are instructions like this one, where the parenthesis here means reference. So add the content of the register addressed by R5 to the content of the register added to R. Okay, anyway, these are details. The thing here is that the language gives you the construct, and the language of the hardware machine is a very simple language, the assembly language. And of course, the set of possible instructions depend on the physical machine that you are trying to build. And again, the interpreter, we already said that we have seen that the interpreter is formed by 4 groups of operation. We have the primitive operation, and we've seen the register that was in charge of that, the arithmetic logic unity. There is the group for the sequence control, and in the case of a CPU, this is taken care by the program counter register. Now, operation in this group are typically increment by 1, but there are also more complex operations for jump instructions in case of conditional instructions like if then else or loop. Data transfer control is implemented by means of registers, and the memory management. In the simplest case, as I told you, there is no need, even if in the reality there is some multi-programming to be implemented. So sometimes, typically, actually, new architecture, they also have some special data structure for managing memory management, but this is not in that schema. That was the very simple case, okay? Any questions so far, guys? Everything is smooth and fine. Cool. Yes, the interpreter is implemented. The fetch, decode, execute loop is implemented into the control unit. And we can see an instance, an example of this loop for this machine that we are considering, the hardware machine, the processor, basically. The fetch phase, next instruction. The interpreter, the control unit, read the address from the program counter register and fetch the instruction from the external memory. The instruction is stored into the instruction register and then is decoded by means of circuits, okay? Combination of circuits is decoded into the hardware. And the execution phase is just the execution of the hardware that decodes the instruction. Yeah, you can see the fetch loop here. The fetch decode loop, execution loop. Here there is the address. So the control unit retrieve the next instruction from the main memory and store it in the instruction register. This is the fetch phase. Then the instruction is decoded into the arithmetic logic unit by means is decoded into the hardware. Okay. Also, operands are fetched and stored into the register So when you have the instruction here and the operands here, you can just execute the instruction. Okay. Eventually, the output will be transferred in the main memory, and the next instruction is retrieved looking at the program counter register. Is it clear, the loop, or we can go through it again? Okay, we're gonna see how to implement a language. What does it mean to implement a language? Okay, to implement a language. Well, but we will come back again on this later in the next class. Okay. Okay, we say that abstract machine allows you to execute a program written in a given language, L, the machine language, and so there is this correspondence. Every machine, every abstract machine understands only one language. That is the language the machine is implemented for. Okay, so machine, one language. On the other hand, for a given language, you can implement several abstract machines. You can see that, and you can implement them. You can implement several abstract machines that they will behave the same if you think in what they will compute, if you think in the output that they will give, but they can be implemented differently with different algorithms, different data structure. Okay, so the correspondence is 1 to n. One language, several machine, one language. Okay. Now, implementing a programming language means to implement an abstract machine for that language. So that it means to implement the data structure and the algorithm that are able to execute the instruction of the given language L, the machine language. Okay. And this basically means to build an interpreter or a compiler of a language. Okay, this is, well, there are three options to implement a language. You can implement a language in hardware. You can implement a language by building a software abstract machine. So you have hardware, software, and then you have a compromise, a firmware implementation. Okay. As I told you before, it's typically abstract. When we talk about abstract machine, we refer to software implementation. So the second group. And this is what happened with compilers and interpreters. What does it mean to implement an abstract machine in hardware? You can give me some feedback on this question, I think. Yeah. What can you tell me an example of a hardware implementation of an abstract machine? Turing machine is a really abstract. It's not hardware. I mean, there is no hardware. You know, it's not implemented in hardware, Turing machine. Exactly. It's what we just saw. The implementation of the CPU that we've just right now seen is an implementation of a abstract machine in hardware. So what you have to do is to implement in hardware the data structures and the algorithms. And we have seen before that the data structure are implemented physically by means of registers, and the algorithms are implemented physically by by using the hardware, the circuits, electrical circuits. Okay, there are advantages of implementation of abstract machine in hardware are efficiency, basically. Since the input language is hard-coded in hardware, it's more efficient because there are no phases in the middle. Okay, so hardware implementation gives you the maximum level of efficiency. Disadvantages. First, the machine is hard-coded, so it's basically impossible. There is basically no flexibility at all. It's impossible to maintain, to modify. So normally they are not, well, let's say that there is no flexibility at all. And normally the language that you have in input, the machine language, is very far away from, is very high level, is very user-friendly, that is very far away from an hardware implementation. So it's very hard to implement an abstract machine in hardware for a high-level language. That's why hardware implementation of abstract machine are typically built for low-level languages. Yeah, low-level languages construct are very close to the physical devices. Typically, for example, assembly language. Then there is software implementation of abstract machines. What you do basically is to implement a program written in a language using constructs of another language. In this case, for example, formally, you want to build a machine for the language L using constructs, programs written in a language L prime. Okay, so you are building an abstract machine written in the language L prime, for the language L. Okay, and this is what compiler and interpreter do. So that's why you can see now maybe more clearly the correspondence between this notion of abstraction mechanism, abstract machine, and implementation of programming languages by means of compiler and interpreter. Okay, this approach gives you flexibility because you are basically translating. Let me say that. Yeah, you are not hard coding your input language in hardware. You are just making a translation of language in another language. And these two languages are typically close in the meaning that if you want to implement a very high-level language in a machine language, in a hardware, the distance between these two languages is they are very far away, metaphorically speaking. One is very user-friendly, and another one is very machine-friendly. Here, you have very close languages, and there is much more flexibility. The drawback is in performance, because you add steps between you and the real execution in hardware. So typically, the performances are not that good as the hardware implementation. A compromise is firmware implementation. Firmware is a language, is not an hardware implementation, but is a very, very low-level language that is not stored in the memory, in the main memory. It's stored in special memory that is typically read-only. So it's a compromise. There are better performance than software implementation, but less flexibility. Then software implementation, and vice versa. Is more flexible than a hardware implementation and less with the worse performances. So which is, of course, you choose one of the three depending on what you want. But for the sake of this course, we just exclude direct hardware implementation. We will see how you will have actually to implement a language, and when we talk about that, we mean software implementation, okay? So when we talk about software implementation, now we're going to focus on software implementation. There are two extreme cases. First is the purely interpreted approach. That is what we commonly call interpreter. And then there is the purely compiled approach, the compilers. And then we will see why we stress this purely interpreted and purely compiled. Okay, do you guys know very intuitively which is the difference between interpreter and compiler? I will not ask you the difference. Just, do you know very intuitively the differences or not? Okay, if there is, okay, who doesn't know at all? Just, I guess, okay. There is somebody that knows? No, okay, you know that. Okay, I promise I will not ask you, so no problem. The difference, at a very intuitive level, a compiler will take the programming input, will produce will translate it in a new program in a low-level language. Okay, so you have a program in a language. The compiler builds you a translation, builds you another program in another language. Okay, the interpreter, on the other hand, will take the input program and instruction by instruction will translate and then execute the instruction. So interpreter do not produce another program in another language. Okay, compiler receive an input program in a language and produce another program in another language. Interpreter receive a program and instruction by instruction at runtime will execute the right instruction to translate. Okay, so interpreter do not produce another program. This is very intuitively speaking, and this is the schema of a purely interpreted implementation of a language. You have your programming input, you have your input data, and this is basically what we saw before. It was a purely interpreted implementation. There is this cycle that you fetch the instruction and you execute and then you output the data. Okay, so input is program and input data, and the output is just the output. Formally, the definition of an interpreter is this one. An interpreter for a language L is the machine language, written in LO. LO is the language that you use to implement the abstract machine. So LO would be the lower level language and L would be the high level language. An interpreter for L implemented in LO is a function that takes in input a program written in L, takes in input also the input over which you want to execute the program. You want to execute PL over the input over this input. So these two are fed into the interpreter that will produce the output of executing the input over the program P. Okay, it's normally it's not that clear, but you will see better later with the difference, okay? Let me just, let's see what happened on the other hand with a compiler. You have, again, you have these two inputs, okay? The program and the input data. You want to execute this program over this input data, but you can see that the compiler receives only one input, that is the program. The compiler translates the whole program into a new program, and then the input is given to this new program. Okay? So formally, the definition is different because you have that a compiler for a language L, the machine language, implemented in the language LO, is a program that implements this function. It takes one program in the language L and produces a program in the second language, LO, the lower level language. But the new program must satisfy this condition. That means if the output, if the compiler produces the program PCLO, this condition must satisfy. That is, the output of the two programs on the same input must be the same. It's a bit technical if you see like that, but basically it's what I told you before at a very intuitive level. Interpreted, you have your program, your data input, and you execute it instruction by instruction by producing the output. And you do not produce a program. Compiler, you take an input, a program, you transform it into another program, and then you give the input to this new program to execute it. Okay, and then if you will check the formal definition, when you have a bit more time, you will see. Okay, are you getting some of that? Or thank you. So, purely interpreted approach, programs are not explicitly translated because you don't build a new program, as I told you. Yeah, the interpreter simply translates instruction by instruction. And when you have a compiler, again, you take the input, the high-level language, and the program, you translate it, and then you will produce a new program. Now, which are disadvantages and advantages of the two approach? Let's try to guess them. What are the? Which one? Exactly. And why? Exactly. So the compiled approach gives you faster runtime, greater efficiency, because with interpreter you have, when you are in runtime, you have to perform again the translation for each instruction. So the translation is done runtime. With a compiled approach, you do the transformation at the beginning, and then when you execute, you don't have to translate anything. Okay, you can see that. As always, where there is advantage, there is disadvantage, and the advantage of an implementation are that first, it's easier to implement an interpreter than a compiler, and then there is flexibility in an interpreter, because the interpreter, when you interpret a program, you are bounded to the flow or control of the program, so it's very easy to spot to debug the program. When you are executing a compiled program, you are executing its translation, and you lost completely the source, any reference to the source program. Okay, this is an example. The language P1 is the program in the input language, in the machine language, is a loop for I from 1 to n, just execute C. That is some block of codes. This language is, this program P1 is translated in a lower level language, P2. The program P2 is the translation of P1, okay? If you can see it's the implementation of the loop. R1 is assigned to 1, and then R2 is assigned to 2, and then you check if R1 is greater than R2, then you go out from the loop. Let me. Do you see that this is the implementation of a loop, right? Okay. Well, in a compiled approach, the compiler will produce a file with this code P2. In the interpreted approach, you will not. The machine just will execute this instruction, but will never produce actually this program. Okay? It's a bit clear, maybe, or not. You can tell us your doubts if you want. So details are not important here. This P2 is the translation of P1. You can see that. Just with a compiled approach, you will produce a file, and then you will execute this file. With an interpreted approach, you will not produce this file. Just the machine will produce and execute one instruction.
P2 is assembly, right?
Say it again?
Is it assembly, P2?
No, it's just, it's not assembly. These are not real languages. It's just pseudocode. These are, actually, you can see that it's kind of it's not that low-level language, because assembly is like the one that we saw before, other one or two. Well, we have seen let's say that for today it's enough, and we will continue. We will take again. We will say again. We will go through this again.